Welcome to chapter 20 of our CNG 4351 Traffic Engineering Operation and Control. This is the last chapter of the class, and we will be talking about basic principles of intersection signalization. The outline for this chapter, we're going to start with some of the revision of some of the terms and definitions that we may touch upon in the previous classes, and then we're going to talk about discharge headways, what do we mean by saturation flow, lost time, and the capacity of the intersection. And then we also will define the critical lane and time budget concepts, and then we're going to introduce you to the concept of delay as a measure of effectiveness and how can we measure the delay at any intersection. First, let's start with some terms and definitions that we will end up using when we talk about the intersections and how can we talk about a signal cycle. So what I mean by cycle, a cycle is simply a single cycle is one complete rotation through all of the indication provided. So if you start with a green light until the green light come back to the same location again, that would be considered a full cycle. The cycle length, and therefore it would be defined as the time in seconds that it takes to complete one full cycle of indications, and typically it's given a symbol of capital C. Every cycle has intervals. So what do I mean by interval? Interval is the period of time during which no signal indication is changing. So interval is considered to be the smallest unit of time described within a signal cycle, and there are several types of intervals within that cycle. We may have the very first interval is the change interval. Change interval is basically the yellow indication for a given movement. This is the time where we see a yellow indication. It's really part of the transition from green to red, in which the movements are about to lose green, and therefore we give them the yellow time or the yellow signal, while all other movements have a red signal. This type of interval, which is the change yellow interval, it's timed to allow a vehicle that cannot safely stop when the green is withdrawn or when the green is done to enter the intersection legally, and the change interval is typically given a symbol YI because it's the yellow time. Another type of interval among a signal cycle is the clearance interval. The clearance interval is also part of the transition from green to red for a given set of movements, and this interval happened during the clearance interval. All the movements have a red signal. So all the movements across the intersection is red, or we call it all red. It is timed to allow a vehicle legally enters the intersection on a yellow to safely cross the intersection before conflicting flows are released. And that's why we typically use the symbol ARI. AR stands for all red. That means at certain time there will be a red signal for the entire intersection to allow those drivers who entered the intersection while it's yellow to complete their movement and clear the intersection before the green is given to the opposite movement. The third interval under the signal cycle is the green interval. The green interval, each movement has one green interval during the signal cycle. During a green interval, the movements are permitted, the ones that have the green light, while other movements have a red light. So if you see that you have a green light, you know that you are the only direction that you're supposed to move, and other conflicting locations or other conflicting movements will have a red light to allow you to cross the intersection safely. The green interval is given a symbol GI for movements. The last and the fourth interval is the red interval. Each movement has a red interval during the signal cycle. All movements are not permitted during this red light, while those permitted to have a green light. In general, the red light interval overlaps the green, yellow, and all red intervals for all other movements in the intersection. And when it comes to the symbol for this type of interval, we use RI indicating for red interval. Another definition under the signal cycles is the phase. The phase is simply, it's a signal phase consists of a green interval plus the change and clearance interval that follows it. So a phase is pretty much a combination between green plus change and clearance intervals that comes after it. So what are the types of signal operations that we typically have? Traffic signals in general at individual intersection can operate on a permitted basis or may be partially or fully actuated by arriving vehicle or pedestrians that they can be sensed by detectors. So the very first type of signal operation is pre-timed operation. Pre-time operation, basically the cycle length, the phase sequence, and the timing of each interval are always constant. That means each cycle of the signal follows the same pre-timed and predetermined plan. It's not gonna change if you change the daytime to nighttime, weekends to weekdays, special occasions. If the signal is programmed using a pre-timed operation, it's gonna be the exact same thing every single time you go through that intersection. Modern signal controllers nowadays allow different pre-time settings to be estimated. That means an internal clock is used to activate the appropriate timing for each defined time period. In such cases, it's typical to have at least an AM peak, a PM peak, and an off-peak signal timing. So now instead of having one pre-timed setting, we can have now with the new technology and the advancement in controllers of those signals, we can have a preset different pre-timed operations. So it's still pre-timed, it still doesn't change by changing the volumes of the vehicles at certain timing, but at least there are certain pre-timed settings for the AM peak, the PM peak, and even the off-peak signal timing. The second type of signal operation is semi-actuated operations. In this case, the detectors are typically placed on the minor approach to the intersection. There are no detectors on the major street, however. So the light is green typically the light is kept green for the major street at all times, except when a call or actuation is noted on the minor approaches. So that means it's always going to be green for the major road until there is a detector on the minor street indicating that there is a vehicle or more wants to cross the major street, and therefore now it's time to give the minor street some minimal amount of green time to allow the accumulated vehicles to cross the major road. This type of semi-actuated operation also subject to limitations, such as the minimum major street green. The green is transferred to the minor street. The green returns to the major street when the maximum minor street green is reached, or when the detector senses that there is no further demand on the minor street. Moving now to the most sophisticated type of signal operation is the fully actuated operation. That means now every lane on every approach must be monitored by a detector. This is going to indicate that the green time is really now going to be allocated in accordance with the information from detectors, and programmed rules has to be established in the controller in order to capture and retain the green time. So for fully actuated operation, now we're going to have the cycle length, the sequence of the phases, and the green time split may vary from cycle to cycle depending on the demand that we have at that intersection. So one more time, there are three types of signal operations. First one was pre-timed, second is semi-actuated, third is fully actuated operation. Now when it comes to how we treat left turns and right turns at any intersection, the modeling of any signalized intersection operation would be a straightforward process if left turns did not really exist. But as we all know, left turns exist, and with so many cases we would desire to take a left turn at any intersection, and those left turns typically are signalized at any signalized intersection can be handled in one of the three following ways. The very first way to deal with a left turn, we're gonna have permitted left turn. When I say permitted left turn, it means it's that one that is made across an opposing flow of vehicles. So a permitted left turn movement is one that is made across an opposing flow of vehicles. This means the driver is permitted to cross through the opposing flow, but must select an appropriate gap in the opposing traffic stream through which to turn. So that means now it's the responsibility of the driver. If they want to take a left turn, they need to watch the upcoming opposing vehicles movements, and now they need to make a decision if once they have now enough gap to the opposing movement, then they can turn left. It's again, this is the least amount of operation when it comes to left turn. We can move to the second level, which is protected left turn. Protected left turn is made without an opposing vehicle flow. That means that the signal plan protects the left turning vehicles by stopping the opposing through movements. This typically requires that the left turns and the opposing through flow be accommodated in a separate signal phases, and therefore is going to lead to multi-phase. That means more than two type of signalization. When it comes to the third treatment for left turns, we call it compound left turns. Compound left turns are more complicated. Signal timing can be designed in which the left turn are protected, which is level 1 of the signal cycle in some time, and they are permitted in another portion of the cycle. So among the same cycle, I have sometime the signal is going to work as a permitted left turns, and another portion of the cycle we're going to have a protected left turn, depending again on the need. So now let's move on to defining other terms that we are going to be using here in intersection signalization that we may introduced it before, and that is the discharge headways, the saturation flow, lost time, and capacity. The fundamental element here of any signalized intersection is really the periodic stopping and restarting of the traffic stream. So typically at any intersection, when the light turns green, there is a queue of stored vehicles that were stopped during the preceding red interval, and those will be waiting to be discharged. As the queue of the vehicles moves, the headway measurement are taken as follows. How do we measure the headway? The first headway is typically the time lapse between the initiation of the green signal and the time that the front wheel of the first vehicle crossed the stop line. While now the second headway is going to be measured as the time lapse between the time that the first vehicle's front wheels cross the stop line and the time that the second vehicle's front wheels cross the same stop line. And afterwards there will be subsequent headways are similarly measured. Let's take a look at this schematic here to show you the difference between the first headway and the second headway, and then once we head now to the fourth and fifth and sixth vehicle, and what's the impact of the headway on those vehicles. So the very first vehicle, as we see here, typically the very first vehicle, it is going to have the highest headway, because now the very first vehicle, the observer or the driver need to observe the signal. Once it starts to turn green, the driver has to hit the hit on the gas, and now he or she wants to accelerate to reach the maximum speed. So that time to accelerate is going to take some time for the first driver to react to the green light, and therefore the headway for the first driver is significantly higher than the second and the third. The second driver now is going to have less amount of headway, as you could see here, because now he or she are realizing that it's green, the first vehicle is already moving, so the second is better to move as well. But still it's considered to be a little bit high compared to once now we reach to the fourth, fifth, sixth, all the way to the ninth vehicle, where now the headway pretty much is gonna be uniform and constant, back to constant until we hit the red light again. So this is what we call, once we hit now that uniform headway, we call this saturation headway and saturation flow rate. As noted before, the average headways tend toward a constant value after the first couple vehicles. In general, this occurs from the fourth or the fifth headway position. So the constant headway can be achieved afterwards and is referred to as the saturation headway because it is the average headway that can be achieved by saturated, stable moving queue of vehicles that they are going to be passing through the signal. Headway is typically given a symbol of H, and the units for headways are seconds per vehicle. How much time it's going to take every vehicle to cross the beginning of the signal. So how can we relate the headway to the saturation flow rate? The saturation flow rate is S is defined to be equal to 3600 over H. What's 3600? This is 3600 seconds per hour. So if we divide 3600 over the average saturation headway in seconds per vehicle, we will be able to get the saturation flow rate, which is vehicles per headway green per lane. And H is the saturation headway, which is seconds per vehicle. Saturation flow rate can be multiplied by the number of lanes provided for any given set of movements in order to obtain the saturation flow rate for the lane group or approach. So let's say if we're having 2 or 3 lanes, we can do this for one lane and then multiply by how many lanes do we have for certain approach, and that's going to give us the total saturation flow rate for the entire approach or entire movement. Now let's talk about some of the time that we lose at the beginning of each cycle, and this is again related to the first and second, especially the first couple vehicles where they encounter what we call a startup lost time. The first couple vehicles, the headway for especially the very first vehicle is actually greater than H seconds, greater than the saturation headway. So typically we say that the first 3 or 4 headways involve additional time as drivers react to the green signal and then they start to accelerate. So the additional time involved in each of these initial headways, which are beyond the typical H or the saturated headway, is noted by the symbol delta I. Delta I is simply the incremental headway for VI. So these additional times has to be added and referred to the startup lost time. So L1, this is what we call the startup lost time. Once we have a green light, we're gonna have some time lost and that's gonna come from the drivers of the first 4 vehicles or so to react and accelerate their cars by the time they see the green light. So how to calculate the L1, which is the startup lost time? It's simply the summation of the incremental headways for a certain amount of vehicles. Thus, it is possible to, now we can model the amount of green time required to discharge a queue of N vehicles. How can we get Tn? Tn is basically the green time required to move the entire queue of N vehicles through a signalized intersection. Simply now it's going to be L1, which is the startup lost time that we got to know, plus N times H. N is the number of vehicles at any certain queue times the saturation headway, which is seconds per vehicle. If I know the lost time coming from the first 4 vehicles or so, plus now the average headway or the saturation headway times the number of vehicles at that queue, this would be now the required amount of green time to move the entire queue during the green light. Another lost time that we typically face at any intersection is what we call the clearance loss time. The startup loss time occurs, as we talked about it previously. It happens every time a queue of vehicles starts moving on a green signal. There is also another loss time associated with stopping the queue at the end of the green signal. This time actually now is more difficult to observe in the field, since it really requires that the standing queue of the vehicles be large enough to consume all the green time provided. In such a situation, the clearance loss time, which we call it L2 loss time, is defined as the time interval between the last vehicle's front wheels crossing the stop line and the initiation of the green for the next phase. So basically the clearance time occurs each time a flow of vehicles is stopped. So now looks like we have two types of loss times. So the total loss time now can be defined. So if the startup loss time occurs each time a queue starts to move, and the clearance loss time occurs at the end, so it happens when the flow of the vehicle stops, then each green phase has to include both. So TL, this is the total lost time per phase, so we have to include L1 and L2. The concept now of lost times leads to the concept of the effective green time. So the effective green time, now we need to include the G time plus L1 and L2, like what we're gonna see in the next slide. But we just, as a reminder, the actual signal goes through a sequence of intervals for each signal phase. We go from green to yellow, all red, and red. So now at any given set of movements, the effective green time is really the amount of the time that vehicles can move. Therefore, the effective red time is the amount of time that they cannot move. So this is going to help us to define what's the effective green time. Effective green time is really related to the actual green time as follows. GI, small gi, is basically the effective green time for movements, and that has to be equal to capital GI, which is the actual green time for movements, plus YI, which is the yellow time, or basically the sum of yellow time and all red time, which is here capital YI is YI, the yellow time, plus the all red time, minus the TL, which is the lost time, the total lost time. So in other words, the effective green time that vehicles are gonna feel while they are standing in the intersection is gonna be the summation of both the actual green time, the yellow time, and all red time, minus any lost time, which are gonna be again two sources, L1 and L2, which they are summed up under this term TL. Another definition here that we need to talk about is the capacity of the intersection and the capacity of an intersection lane or lane group. So we know that the saturation flow rate represents the capacity of an intersection lane or lane group, assuming that the light is always green. When I say lane group, that means, let's say if you're heading northbound or you're having 2 or 3 lanes through movement, we call those as a lane group because they're gonna lead us to the same direction, and there is no difference between lane 1, 2, and 3. Of the 3 of them are through movements, not turning right, not turning left. They're just having the 3 movements all in one direction. So the portion of real time that is effective green is really defined by the green ratio. So the ratio of the effective green time to the cycle length of the signal. That's why we call this ratio G over C. The capacity of any intersection lane or lane group may be then computed by this equation here. We're having CI, which is the capacity of a single lane or a lane group, times GI, which is the effective green time, which we defined it already, over capital C. This is the signal cycle length. So if you make that ratio between the effective green time over the overall signal cycle length, times the saturation flow rate for a lane or lane group. This is going to give us the capacity of that lane or lane group. So let's have now a problem to understand the definition that we already have so far. So let's consider a given movement at the signalized intersection with the following known characteristics. So if I'm telling you that this cycle length is 60 seconds, the green time is 27 seconds, the yellow plus all red time, which is the capital Y, 4 seconds, the saturation headway, which is H, is 2.4 seconds per vehicle, the startup loss time, which is L1, is 2 seconds, and the clearance loss time is 2 seconds. Now the question would be, for these characteristics, what is the capacity per lane for this movement? So let's go ahead and start to solve this problem. The very first step here that we need to think of is, once the amount of the time per hour used by vehicles at the saturation flow rate is established, then the capacity can be found by assuming that this time is used at a rate of one vehicle every h seconds. So because the characteristics stated are given on a per phase basis, this would have to be converted to a per hour basis. In fact, this is easily done knowing the number of signal cycles that occur within an hour. So in our problem here, we have 60 seconds per cycle. Therefore, there are 3600 over 60, and that means that there are 60 cycles within this hour. The subject movements will have one green phase in each of these cycles. If we know all this information, now we can tell that the time in 1 hour is 3600 seconds. The red time in 1 hour is simply 60, which is the overall cycle length, minus 27, which is the green time, minus 4, which is the two lost times added together, times 60. So that's gonna give us 1740 seconds. The last time in 1 hour is also 2, which is the startup, plus the clearance lost time. So 2 plus 2 is 40, times 60 seconds, 60 cycles per hour. That means there will be 240 seconds lost per hour. Therefore, this can give us now the remaining time in an hour, which is the green, or the effective green time, which is 3600, minus 1740, which is the red time, minus 240, the lost time, and this is gonna be equal to 1620 seconds. The 16 and 20 remaining seconds of the time in the hour represent actually the amount of the time that can be used at a rate of one vehicle every h seconds, where h, which is the headway, is 2.4 seconds per vehicle in this case. That means now we can get really the capacity of this movement can be computed as C. The capacity is going to be equal to 1620. Those are the 1620 green time, and every vehicle needs 2.4 seconds, and therefore the capacity is going to be 675 vehicles per hour per lane. Another approach that we can solve this problem is if we can use the equation 20-6 with the following values. So S here, this is 3600 over 2.4 to give us here the kind of the density. So I have 3600 seconds per, or divided by 2.4, which is the headway. This is giving us, I'm gonna have 1500 vehicle per hour per lane. And now I can get the effective green time, which is 27 seconds the green, plus 4, which is the yellow time and the all red time, minus 4, which is 2 seconds each for the last time that we have every cycle, and therefore the G, the effective green, is 27 seconds. So now I can get the capacity is equal to 1500, which is the theoretical capacity, if you will, times the actual ratio between the green time over the overall length of the cycle, and that's going to give us the same answer, which is 675 vehicles per hour per lane. So as you could see, there are two ways of getting the same number, and you would pick whichever way you feel comfortable with. Now we're gonna move on to the concept of critical lane and time budget concept. So how can we now assign that effective green time to all the different movements? In signal analysis and design, the critical lane and time budget concepts are very closely related. The time budget is simply the allocation of time to various vehicle and pedestrian movements at intersections through signal control. Time is constant. There will always be 3600 seconds in an hour, and all the movements must be allocated within this 3600 seconds. This is your overall budget, and at any given hour, time has to be budgeted to legal vehicle and pedestrian movements, and also we need to consider the lost time that we're going to be facing. Now, the critical lane concept actually involves the identification of specific lane movement that will control the timing of a given signal phase. So for example, in this case here, we're having this lane 1, this is going to be the governing or the critical lane for this path, the north and south bound, and this lane 2, this is going to be the critical lane for the east-west bound. So signal timing for this case and design must accommodate the total demand flows in lane 1 and 2, because these lanes have the most intense demand. Therefore, if the signal accommodates them, that means all other lanes will be automatically accommodated as well. So while we're trying to work in establishing the time budget for the intersection, time would have to be allocated to 4 elements. First, movements of vehicles in critical lane 1, movements of vehicle in critical lane 2, and also we need to consider the startup and clearance loss time for vehicles in critical lane 1, as well as the startup and clearance loss times for vehicles in critical lane 2. So how can we bring all these 4 elements together in one aspect? This is here we are gonna talk now about the maximum sum of critical lane volumes. So by definition, each signal phase has one and only one critical lane, except for loss times in the cycle where one critical lane is always moving. Loss times occur for each signal phase, and it's basically try to represent the time during which no vehicle in any lane are moving. The maximum sum of critical lane volumes may therefore be found by determining how much total lost time exists in 1 hour. So the remaining time, which is the total effective green time, may then be divided by the saturation headway. This is again we're getting closer and closer to the concept of the maximum sum of critical lane volumes. It is assumed that the total lost time per phase, which is TL, is a constant for all phases. If we have that assumption, then the total lost time per signal cycle is capital L. It's equal to capital N times TL. What does that mean? It means the capital L, the total lost time per cycle, is going to be equal to the number of phases in the cycle times the total lost time per phase. So number of phases times the lost time per phase, that's going to give us the overall lost time per cycle. Now also can define the lost time per hour. The total lost time in an hour would depend on the number of cycles occurring in that hour. So, and this is where we come up with this equation. LH is the total lost time per hour. It's going to be equal to L, which is lost time per cycle, times 3600 over C. What's this ratio here? This is to define how many cycles am I going to have for every single hour. So if I have 60-second cycle, that means the total lost time per cycle has to be multiplied by 60 cycles per hour to give you the overall lost time per hour. But again, the C, which is the cycle length, may vary between 30, 90, 60, or even up to 120 seconds. So we need to know the cycle length. Now we can divide 3600 by the cycle length, multiply that by the total lost time per cycle to give us the overall lost time per hour. And the units is going to be seconds per hour. Now the remaining time within the hour is going to be devoted to effective green time for critical lane movements. And this is going to lead us to this little equation here, which is TG, the total effective green time in 1 hour, is equal to 3600, which is the entire budget of 1 hour, 3600 seconds, minus LH, minus the total lost time in 1 hour. This is going to give us again the total effective green time in that hour. This time, which is TG, may be used to calculate the rate of one vehicle every H seconds, where H is the saturation headway. So VC is the maximum sum of critical lane volumes, vehicles per hour, is equal to TG, which is the total effective green time, over the saturation headway. Now from these two equations, now the following relationship can be developed. VC, which is now the overall maximum sum of critical lane volumes, is equal to 1 over H, the reciprocal of the headway or the saturation headway, times 3600 minus N, which is how many phases, times TL, which is the lost time, times 3600 over C. If we apply this equation, it should be able to give us the maximum sum of critical lane volumes. Let's have an example here to understand the concept of the maximum sum of critical lane volumes. So if we're having this example here, if the signal at this location has 2 phases and the cycle length is 60 seconds, and it's also given to you that the total lost times of 4 seconds per phase, and the saturation headway is 2.5 seconds per vehicle, find the maximum sum of critical lane flow. So all the information pretty much are given to us, and we need now to just make use of the equation that was shown in the previous slide. VC is going to be equal now to 1 over the average or the saturation headway times 3600, this is the total budget in 1 hour, which is 3600 seconds, minus 2 times 4, two phases, as it's shown here, or having 2 phases per cycle, times 4 is the total lost time per phase. So overall we're going to have 8 seconds of lost time per cycle, times how many cycles per hour, which is 3600 seconds over 60 seconds. And this would lead us to the answer, which is we're having 1248 vehicles per hour as the maximum sum of critical lane flow. Let's take a look at this relationship now, which is the relationship between the cycle length and the sum of critical lane volume, as well as how many phases we may have per cycle. As we could see here from this graph, we can conclude that as the cycle length increases, now cycle length increases from here to here, for example, as the cycle length increases, the capacity of the intersection also increases. As you could see, if I have a slow or low cycle length, I'm going to have now the sum of critical lane is at this level, where now if the cycle length increased, it's going to have a huge increase of the critical lane volume as well. This is because of the lost time, which are constant per cycle, are going to be reduced. What I'm trying to say is, now if I have the cycle length from 30 seconds to 60 seconds, that means in 1 hour I'm going to have 60 cycles rather than 120 cycles per hour if the cycle length is 30 seconds. So what does that mean? I'm reducing the number of cycles, and if I'm reducing the number of cycles per hour, that means the lost time, which is pretty much constant per cycle, is going to be reduced significantly by increasing the cycle length, and therefore the capacity or the sum of critical lane volume is going to increase. Please also note that, however, the relationship gets flatter as the cycle lengths increase. As you could see, after we reach here a high cycle length, now the relationship is getting flatter. That means if I increase now the cycle length to more than what I need, it's not going to improve any more the critical lane volume. Another observation, capacity rarely can be increased significantly by only increasing the cycle length. That means increasing the cycle length is not the only solution. Sometimes we're going to reach certain high cycle length beyond which I cannot increase it anymore, and therefore we need to look for other measures such as adding lanes to solve that problem. Now we're going to shift gears to how can we find the appropriate cycle length. So the very first equation that we're going to learn to determine the cycle length is the minimum acceptable cycle length. The minimum acceptable cycle length is this equation: C minimum is equal to n number of phases per cycle times TL, which is the number or the amount of lost time per phase, over 1 minus VC, the volume and the critical lane, over 3600 over H, which is the saturation headway. So if I give you an example saying that the actual sum of critical lane volumes was determined to be 1000 vehicles per hour, what would be the minimum feasible cycle length? Based on the previous information and what we have now, C minimum is equal to 2. We're having 2 phases, and again this is a continuation from the previous example. 2 phases times 4 seconds, which is the total of lost time, over 1 minus 1000, which is now, this is what's given, 1000 vehicle per hour, over 3600 over 2.5, which is saturation flow rate. And now I'm saying that the minimum cycle length, the minimum acceptable cycle length, is 26.2 seconds. While the previous equation might not be related to the real life examples, this minimum cycle length might be a very theoretical equation. In general, signals would be timed for the flow rates occurring in the peak 15 minutes of the hour. Therefore, the previous C minimum equation could be modified by dividing by a known peak hour factor to estimate the flow rate in the worst 15 minutes period of that hour. In a similar fashion, most signals would be timed to have somewhere between 80 and 95% of the available capacity actually used. You don't want to use 100% of the capacity. You don't want to assume all the time that the intersection is gonna be jammed and we're reaching 100% of the capacity of the network or of the intersection. Therefore, now we're gonna be modifying the C minimum equation to more of a reliable equation, which is CDES, C desired, which is the desired cycle length. The desired cycle length is simply now n times TL, which is the number of phases per cycle, times the lost time per phase, over, now we're doing 2 modifications here. 1 minus VC, same thing, 3600 over H, that's the same, and now we're including PHF, which is the peak hour factor that we need to include. We're gonna pick now the worst peak hour factor and multiply this also by V over C, which is the desired volume to capacity ratio. So it can be 80%, it can be 85, 90, 95%. Typically we try not to reach, or we try not to design the signal timing based on 100% volume to capacity ratio. So let's here have an example and see how can we get the desirable cycle length. If the peak hour factor, based on the previous example, we're building on it, if the peak hour factor is 0.95 and it is desired to use no more than 90% of the available capacity during the peak 15 minutes period of the hour, then now C desirable is going to be equal to 2 times 4, 2 phases times 4 seconds lost per phase, over 1 minus 1000 over 3600 over 2.5, the saturation headway. Now we're introducing this little guy here, which is the peak hour factor 0.95, and I don't want to exceed 90% of the available capacity, which is 0.9, and now it's going to tell me that the desirable cycle length is 42.6 seconds rather than 26.2, which is the minimum theoretical cycle length. In practical terms, by the way, when it comes to this solution, this would lead us to the use of 45-second cycle length. And it would be now interesting to look at this equation, and how about if we keep changing the the capacity ratio to see the impact of this capacity ratio on the desirable cycle length. The relationship between the desirable cycle length, the sum of critical lane volumes, and the target V over C will be very quite interesting to take a look at it in the next slide. So, as you could see here, we're having in the x-axis the sum of critical lane volume, which is VC, and the y-axis we have the desirable cycle length, and we have different lines. Every line is representing V over C ratio, volume to capacity ratio, and the volume to capacity ratio, typically we go from 0.8, which is 80% of the capacity, all the way to 100% of the capacity. So what do we conclude from here? If we are increasing the sum of critical lane volumes, let's pick certain V over C, let's pick 0.9. And now if I'm increasing the sum of critical lane volume from this much to that much, that means now if I want to increase the critical lane volume, I have to increase the desirable cycle length. Desirable cycle length is going to keep increasing if I really want to improve the critical lane volume. How about if the desirable cycle length is pretty much fixed? Now I want to compare the desirable cycle length if I'm using different V over C. So for example, if the desirable cycle length is this much, and if I'm using V over C is 0.8, then this is going to be the sum of critical lane volumes all the way to 0.95. Now I'm allowing the intersection to use up to 95% of its capacity, therefore I can increase the critical lane volume that much. So let's have here a numerical example to understand the impact of V over C ratio on the desirable cycle length. Consider the case of three-phase signal. TL, which is the total loss time, is 4 seconds per phase, and the saturation headway is 2.2 seconds per vehicle. Peak hour factor is 0.9. VC, the volume is 1200 vehicles per hour. Now we need to get the desirable cycle length, will be computed based on a range of a target ratio based from 1 all the way down to 0.8. So now this is a brand new example, not related to the previous one. Now we're gonna see what's the desirable cycle length if I have three phases. 3 times 4, this is the total lost time per phase, over 1 minus 1200, this is the volume in the critical lane, over 3600 over 2.2, which is the saturation headway, times 0.9, which is the peak hour factor, times 1. 1 now means that I'm using 100% of the capacity. V over C is equal to 100%, and therefore the desirable cycle length is 65 seconds. As we said, in most of the cases we don't want to have the system always using 100% of its capacity. How about if we reduce the V over C from 100% to 95%, as in this example? If you want to reduce it, and now I want to use up to 95% of the capacity of the intersection, then everything is the same, except now I'm going to change from 1 to 0.95, and now as you could see, I need to increase the desirable cycle length from 65 seconds to 85 seconds to handle the same problem. I can keep decrease the V over C ratio to 0.9. 0.9 is going to give me 130 seconds. If I want to use only 85% of the capacity, it can run all the way to 290 seconds. And guess what happens if you put 0.8? If you now put 0.8, which is 80% of the capacity of the intersection, I'm going to get a negative value. What does that mean? That means that V over C ratio of 0.8 cannot be achieved under any circumstances. Any negative cycle length would really tell you that it's not enough time, there's not enough time within the hour to accommodate the demand with the required green time plus the 12 seconds of lost time per cycle. That means if you really want to go to very low V over C, which is 80%, that means now by playing with the desirable cycle lengths, that's not going to be the ultimate solution, and therefore you have to think of other solutions such as adding more lanes. Now let's have another example here to find the appropriate cycle length. So the example here is going to be related to this schematic. Now, using the time budget and the critical link components and concepts that we talked about, determine the number of lanes required for each of the critical movements and the minimum desirable cycle length that could be used in this intersection. A little note here that the initial cycle length, which is specified as 60 seconds, will be changed and will be modified as part of the analysis. So the very first thing that we need to do here is we need to get the maximum sum of critical lanes. V over C is simply 1 over the headway, which is 2.3 seconds as it's mentioned here, times 3600, this is the total budget, 3600 seconds in an hour, minus 2, which is 2 phases, times 4, which this is the total lost time per phase, times 3600 over 60. 60 is the initial cycle length, and that would tell us that we need to have the maximum sum of critical lanes is 1357 vehicles per hour. While, as you could see, the critical lane in this direction is 1200 vehicles per hour, and the critical lane in the east-west direction is 1800 vehicles per hour. So what to do next? So the critical, as I said, the critical southbound volume is 1200 vehicle per hour, and the critical eastbound volume is 1800 vehicle per hour. So the number of lanes per direction now it need to be determined. So whatever combination that we're going to end up using, the sum of the critical lane volumes for these two approaches must be below the maximum flow, which we just calculated, which is 1357 vehicles per hour. So what to do? First, let's assume that we're going to have one lane per direction, or one lane per bound. So if we're using the 1200 and we're using the 1800, that means 1200 plus 1800 is 3000 vehicles per hour, which is way more than what the intersection or what the maximum volume, which is 1357. So that's no good. NG, no good. How about if I have two lanes in the east-west bound and one lane only in the north-south bound? That means now I'm gonna say I'm gonna have 1200 vehicles, because now I'm having only one lane, which is the only critical lane in this bound, and I'm gonna pick one out of the two to be the critical lane. So 1200 plus 900, that's gonna give us a total VC is 2100 vehicles per hour. This is also still higher than the maximum volume that we can handle, which is 1357. That's also not good. Now we're gonna move to, how about having two lanes in the north-south bound and two lanes in the east-west bound? So now the 1200 that was only for one lane, I'm gonna divide it into two lanes, 600 per lane, while the east-west bound I'm gonna having two lanes, so the 1800 now is gonna be 900. So if I sum the 600 plus 900, is gonna give me volume of 1500 vehicles per hour, which is still higher than what I calculated. So it looks like I need to have extra lane. So if I keep on the north-south bound two lanes, each one is gonna handle half of the 1200, while in the east-west I need to now to divide the 1800 vehicles per hour to three lanes. So each lane now is going to handle 600 vehicles per hour. Therefore the summation of the volume of the critical lanes is going to be 600 plus 600, one from here and one from here, and that's going to give me now a total of 1200 vehicles per hour, less than the maximum critical lane volume, which is 1357, and that would be the good design, and that would be the estimate for how many lanes do I have to handle that amount of vehicles at that intersection. Now the next step is to get the cycle lengths and what's the desirable cycle length. So as we said, if the final scenario is provided That means now VC is only 1200. We're not going to reach the maximum, which is 1300 something. So the VC now is 1200 vehicles per hour. Now it is possible that the original cycle length, which was 60 seconds, now we need to revise this assumption. A desirable cycle length is now equal to 2 phases times 4, which is the TL, over 1 minus 1200, which is VC, the current VC based on the number of lanes that we're having, over 3600 seconds over 2.3, which is the saturation headway, times 0.95, this is the peak hour factor, which was given to us, and I'm assuming that let's use the ratio, the capacity ratio of 90%, 0.9. This is now going to give us 77.7, which is roughly 80 seconds. I need to revise the cycle length to the desirable cycle length of 80 seconds. That resulting cycle length is larger than the original 60 seconds simply because the equation takes in consideration both the peak hour factor, which is 0.95, not 1, and the target ratio, V over C ratio. And instead of 1, I'm using now 90% of the overall ratio or overall capacity of the intersection. Additional lanes could be provided in either direction, more than what we decided. So if we decided 3 lanes in the east-west and 2 lanes in the north-south are too little, I can increase those lanes, and if I increase the lanes more than what's required, then this is gonna drop the cycle length quite significantly. So if 80 seconds is too much, I can increase the number of lanes more than what we found out, and then that would be the solution to decrease the cycle length less than 80 seconds. So here, how about another scenario? If the space is limited for both eastbound and southbound approaches to 2 lanes only, so instead of having 3 lanes in the east-west and 2 lanes in the north-south, now let's say I'm going to have 2 lanes only. That's the limitation, 2 lanes in the east-west bound and 2 lanes in the north-southbound. Therefore, VC now is, if you recall, is going to be 1500 vehicles per hour. And the question here, would it be possible to accommodate this demand by lengthening the cycle length? So now instead of having 3 and 2, we're going to have 2 and 2. And let's see now if the desirable cycle length, how can we increase the desirable cycle length to handle this limitation in number of lanes? So C desirable now is going to be 2 phases times 4, which is the total last time, over 1500 instead of 1200, over 36 over 2.3, the saturation headway. Peak hour factor is the same, 0.95, and V over C is 0.9. And guess what? The desirable cycle length now is in negative. That means it's no good. The negative result really here indicate that no cycle length can accommodate the new VC, the new capacity of 1500 vehicles at this location. We cannot do it. If you want to have 2 lanes per 2 lanes in the east-west and 2 lanes in the south-north, that's not going to be enough. And therefore, the minimum number of lanes to handle the amount of traffic at this intersection would be 3 in the east-west and 2 in the north-south. With that, we finish the concepts of the critical lane and time budget concept, and in the next lecture we will be talking about how can we measure the delay and how can we do a delay study at an intersection. Thank you.